Mark Schiller, who's the chair of the lectures committee, could not be here tonight, so I get to introduce myself to introduce Greg. I'm Anders Carlson, for those of you who don't know. And I need to inform you of our lecture series. This is the penultimate one this semester, and I'm giving the last one next week, same time, same place. And enough about me. Our third annual Facade Symposium will also be in this room on Friday, December 2nd. There's a nominal fee, and space is limited, so sign up now. And that's the end of our lecture series for the year. I would now like to introduce USC Assistant Professor Greg Otto, who founded Buro Happold's Los Angeles office in 2006 and functioned as office director through 2008. He is currently leading their West Coast Fabrics team, which is structural and facade engineering. Greg holds degrees from MIT, Cooper Union, both in engineering, and Kansas State University in architecture. Having been educated as both an architect and engineer and engaged in the practice of both, he has been focused on collaboration between the architect and engineer and the potential for innovation that such working brings. His current research is directed toward developing necessary tools and methods to overcome traditional discipline silos to deliver innovation. The work is principally focused on buildings, their design, construction, and operation with strong alignment to ideas on sustainability and performance. Since joining Buro Happold in 2001, he has worked on a diversity of projects that have staying power of the decade, such as the Genzyme headquarters, the Smithsonian Patent Office building, Courtyard Enclosure, the Lara Cricket Academy, and Harvard Allston Science Complex, and numerous others, which I'm sure you'll see. In addition to commercial work, Greg has an impressive academic pedigree. He has been an adjunct professor at Parsons School of Design, Stevens Institute of Technology, and a visiting lecturer at SCIArch, MIT, University of Pennsylvania, Harvard, Yale, UC Berkeley, and University of Texas, covering both subjects of architecture and engineering. His current research is in enhanced data-centric, data-rich environments. Greg is interested in using new media and computing tools such as gaming interfaces and handheld devices to assemble and mine a growing spectrum of data. He has partnered with interactive media artist Scott Fisher of the USC School of Cinematic Arts to create a 3D building lifelog that would allow a building to report on its energy use. He is also currently editing a monograph on engineering complexity in art based on case study projects done in his work studios at Buro Happold. Greg, as you can see, is a polymath who happens to practice structural engineering and has been asked to teach everything but that here at USC. However, he still manages to sneak structures in, such as having students use structural engineering as a fitness criteria for genetic algorithms. Now, Greg also is not shy about expressing his opinion, so here's one of his quotes. Architecture remains principally focused on visualization and has yet to fully exploit the full benefit of computation. The potential to prototype buildings before being constructed will transform an industry that has failed to make sizable productivity leaps in design or construction in the last 2 to 3 decades. With that, I give you Greg Otto.
Thanks, Anders. Appreciate that. Hopefully I can live up to all of that. The title of my talk is Data-Centric Working. This has really been a big part of my focus, really since walking out of college in 2001 from MIT. Data-centric working in a way that actually can develop project-specific design processes. So in other words, talking about bespoke methodologies to deliver projects. And I'll try to explain that through a series of case studies. The first observation, so I had practiced architecture in the 90s with Holt Henshaw Jones, Wes Jones in San Francisco. And some observations that came out of that. Fragmentation in the industry was big then, it's worse now. And there was a serious rift between design and fabrication. In other words, fabrication intelligence was not coming into the design process, and that was problematic, and certainly influenced or disabled designers to have a significant say in how buildings and projects were being built. The next observation I noted in that period of time was really the proliferation of design tools, digital tools, that there were a whole batch of new tools coming out, and people were launching off on these specific tools, and their trick ultimately became the trick of the tool. So Turbo 3D is one that comes to mind, which would allow somebody to facet a corner of a building, and all of a sudden everybody was faceting buildings. And I saw that as a real liability, meaning people were actually learning software and becoming masters of a particular piece of software, but not able to extend it. So I saw that as a problem. The third thing that I observed was really that there was a lack of an integrated design process. So it was nearly impossible to get engineers plugged into anything that I was interested in. So remember, I was an architect at the time, or an architectural designer at the time, really trying to push ideas, and that became a real difficult challenge. So ratchet forward, I go to engineering school after working some construction and other things, and walk into Buro Happold, and it was a great lab, and I had a critique, and this is really my critique. This is the diagram. This is my studio. This is how my studio, design studio, works at Buro Happold, and really is the context for my research. The first piece is any good design approach always starts in research, but research needs to know where it's going, and you need to mine the world of fabrication, construction, materials to understand where you can go forward and where you can actually innovate. The next piece is the mixer, and not necessarily talk, although it's late, we could talk about a gin and tonic, but the mixer really is actually using computation, the analysis, the geometry development, the analysis, the simulation, using those tools to spin the wheel, to begin to suss out what are the big ideas and how I might push innovation forward, and then ultimately going to construction. And this thing is a feedback loop. So the first thing really was, how do I take apart what is traditionally a very linear way, or a very linear approach? You do a schematic design, you do a design development, or you do construction documents, and this thing just kind of pushes along, and it never really allows you to really, truly stir it, and then ultimately it goes out to construction documents for bid, and the contractor comes in, or the fabricator comes in with a whole new way, and you got a whole nother project, yeah? So the work I'm going to show, the case studies I'm going to show you, really are, how do I embed this materials and fabrication logic into digital methods, really test these things for fitness through the analysis and through the simulation, to ultimately arrive at very innovative, very complex projects, but projects that ultimately can be resolved with traditional engineered materials. Some of you have probably seen this project. I've talked about it before, but I think it's exemplar in trying to explain what I'm talking about. This is Janet Eckelman's project in Phoenix, Arizona. Her secret is patience. For those that know Janet Eckelman, she works in netting, fishing, trolling nets. And this is a very, very large one in downtown Phoenix that is effectively suspended by some hoops. It's composed of 3 layers, which is a central cone, an outer structural shell that holds it into place, and then this kind of lofty geometry that almost like skirting. So it's 3 layers. The important part for an engineer is really that middle layer. That's the piece that holds it into shape and gives it its geometric positioning in space. To think that you're going to actually knit something like this and know it absolute, right? Because the building department says, okay, what is it? What is it? Define it. Is it going to actually be like this? How do you do that? You're not going to draw that. It's just not possible to draw that. And so working through digital methods, we did exactly that. We went through and we talked to the fabricators. We talked about how you make fishing nets to understand what fishing nets are. So this is the modern trawling net, or a Euro net. This is a net looming machine. And the only information you need, you can make whatever you want in netting, with the proviso that you can actually give distances between knots. That's all you need. So if I can describe that geometry and I can isolate what the distance are between knots, I can generate any complexity I want. And so that's the process. So arriving at how to get there is the challenge. So there's a looming machine, the netting. And this is just a visualization of an Excel spreadsheet. The Excel spreadsheet was all we had to provide as a deliverable to make the project. The process is we wrote a whole series of scripts that we're going to embed in Revit. So much of what I'll talk about tonight is very much tool development. There is no bespoke piece of software out there that's a solve-all for anything. Yeah? And so I've always had the vision and the position that my studio would be always software agnostic, meaning we're going to use whatever is the best tool at the time, and we're going to mix and match, and what's not available, we're writing. We're going to script it, we're going to code it, but we're going to build that tool to do that process that's going to arrive at the project that we ultimately wanted. So this is the development of that tool in Revit. It ultimately culminated in this piece called the Echelman Net Layout Tool, which is nothing more than a drop-down in Revit, shockingly. And this piece will allow us to describe that geometry, then extend or throw or cast netting across the surface, and then we can find those nodes of the netting. And this just shows how this thing gets woven together. You get layers, so you get rows that are stitched together. And you can see how the coloration. We did a whole series of mock-ups to actually test that the logic held. So in a digital process, something like we're proposing here, you're going to produce an Excel spreadsheet and just run it through the machine and hope you're right. Boy, that's a mistake. Make sure you mock-up. The mock-ups are really important. You test. You always go through this process of digital testing, digital mock-up, physical testing, physical mock-up. So from an engineering point of view, we have to form-find this thing. And we've written a whole bit of software called Tensile, which actually uses dynamic relaxation to relax a surface. And it's really the least energy surface, so think bubble film. It can only be one surface. And so we can form-find these shapes. So we had to form-find this shape because it's a net. It doesn't have stiffness. It's going to fall into shape. So we have to know what the final shape is. And for the artist, they're only interested in the final shape. How you get to the final shape from the shape that you need before it relaxes, that's a challenge. So we had to go through that process. So this is the form-found shape, and you can see it starts to drape. So you see these little puckers coming through. Then the structural netting. This is the piece that attaches to the main ring and then drapes down. This principally carries the structural loads. And then effectively what is the piece, what gives it its form, is these drapes, these pleats that effectively fall down and colored. And the coloration are the strips or the bandings that define it. So you can see the layers building up. So this is a structural analysis. Because it's data-centric, because it's a data-rich environment, we can bring that geometry directly into our analysis software. This is actually Robot, which is Autodesk's FEA solver. And we're looking at stresses within the nylon cords. What's important here is actually, again, that interstitial layer, which is the larger diamond pattern. That's the piece that's actually going to hold it into shape. And so we're just pushing this data between one platform, being Revit, pushing it into the analysis. So we're not creating two models to get that shape. We could then do the analysis or additional analysis after we had that whole piece done. This is looking at wind. So that's 30, 60, and 90 miles an hour wind. Obviously in Arizona, everybody's concerned. So we could understand what that behavior is actually going to be like under these load cases. Any jurisdiction is going to want documentation. So, and whether it makes any sense, whether it really tells a story or not, you still owe documentation. So here's your plan. You get a ring and a ring. You get some pretty pictures. Say, we need some nets. We have distances between knots, so that geometrically describes it. The hoops to tie it all together, and some details. and we pulled a building permit. So we pulled the building permit, and this is the piece actually installed. It's suspended in the air by 3 masts, and then the hoops. You can see the hoops going in. There it's lit up. Inside. It simply arrived in a truck. So they made it in Europe, put it in a container. Container got on a trailer, pulled it out. It took longer to put the masts up and hang the rings than it took to hang the net. The machine knit all of those netting within 2 weeks. So purely off a digital piece. The next project I'm going to show you, it was a competition. This was at CCA, California College of Arts in San Francisco. This is the architecture school there. A firm called Buro gave a proposal. They have the skylight issue, or had a skylight issue. This solved the skylight issue. Very bright light coming through the skylight and creating glare within the space. They wanted to fill it up with something that actually would diffuse the light better. So Buro came up with this design of this faceted kind of paper-like lamp shade piece that was going to fill the space. They won it. They won it with no engineering input or anything like that. Well, a friend of mine, having worked at Wes's office in San Francisco, he called me up and he said, I have a friend at CCA. He won this thing and now doesn't know how to do it. It's a complex thing. It's kind of curvy, doubly curved. What does he make it out of? What's it of? How do you do it? Blah, blah, blah. So we got in touch, or he got in touch with me, and we talked through how we might think about it. And ultimately what we arrived at was, let's make it a cable net, but panelize the cable net, so move away from cables to actually dealing with panels. And I'll talk to you about the process of that. This too is very much a data-centric process. So there's the existing conditions, you know, the geometric configuration of the building, what the aperture of the building is. We got real measurements from that. So we got the building surveyed, that came in, and then we had to right size this piece. If we made the piece too big and it didn't fit the atrium, we would have been in trouble. And it's tight, it's really, really, really tight. So this is the CATIA model that effectively describes the interrelationship between the building and the piece in a sectional case. We work often on these very complex things operationally between Rhino and CATIA from a geometric point of view. It's just a way that we can manage precision, work out some of the ideas, and then lock it in a parametric way. So this is building up the principal geometry of this light shade. So here's the CATIA geometry, defining it, and I'll talk about how we get to the cable net. So CATIA geometry, we've got CATIA geometry, and we're going to import it into Rhino. We're going to tear that geometry now apart. We have the principal lines of curvature between the two openings. These are the hanging points, 1, 2, 3. This ring is actually where to use it to tension the whole thing. So cable nets, if anybody knows what a cable net is, it's got to be tensioned to lock in the pre-tension. And then we got the primary geometries described. Governing geometries, obviously you've got the 3 rings from the top that actually get locked into space, and then the cable net gets hung from that, and then you got the lower ring, which effectively pre-tensions the whole thing. So you've got your governing geometries. We're going to now develop the cable net, which is, we're going to subdivide the geometry, so you can see the subdivision between the geometry, and we're going to break this into node points, equal node points, and then drag a cable net line across, so we got transverse geometry. Now we can panelize this thing. So this is going into tensile, so we have a cable net, and we can actually relax this surface, so we're going to form find this thing. We've got our fixed geometry, which is locked. Yeah, that can't change. It's a rigid element. We have our interface conditions between the primary geometries. We've installed the mesh, because we're going to panelize this thing. We've got the support conditions established, and we form find it. So that's a relaxed shape, right? So everybody saw the thing make the step, the surface make the step. Here you go again. You can see the hard line of the cable net, the principal linking geometry between, and it relaxes. So again, that's dynamic relaxation using tensile. And just one more time, you can see it relax. So now we have all of that. So we found this surface. We have a cable net defined. We now need to do the FEA because we're going to switch out cables, so we can't guarantee that we get pure tensile forces through a cable. We're going to put it through panels. And the trick is we're actually ultimately working towards HDPE, which is a plastic material easily cut from a laser cutter. Yeah? So we can actually panelize this thing. And you'll see the madness in going to that. We want to do some tricky stuff with what the surface ultimately becomes. So we import it into FEA. So it's a nonlinear cable analysis. So we first look at the cable analysis, look at the stress in the cables, look at the jointing, make sure that we get what is the connection between the panels? Is it one revet, two revet? How big is that revet? We get the axial forces defined within the support conditions. So these are cable-tied rings. So here's your ring, here's your cable, that's your fixed point. And then we can find the deflected shape. Ultimately, in these types of structures, you're looking for the solution with the least deflection. Ultimately, a form-found structure has the greatest level of stiffness. The form-found shape has the greatest level of stiffness, and the deflected shape will be the least. So that's the deflected shape. The bending axis, this is bending within that ring. So imagine the cable net's now pulling on that, and that ring is going into compression. Again, major axis bending. Redefined cable net. So we're going through a process of optimization. We're refining that. We're looking for a better performing net, so least deflection, and the deflected shape. And you can see by the coloration from the previous one, which had this fuzzy quality, to this, you can see that we actually tightened this up. And this is enough of an iteration, not perfect, but enough of an iteration we can move forward. So we've now incorporated the material properties into the model and effectively putting in membrane properties. So this is the HDPE plastic. And again, we're going to do this again. So there's got a rigid panelization between, or in each one of those membrane elements, looking at the deflected shapes. You can see this kind of dark shading piece. That's the offset from theoretical, yeah? Or the deflected shape. So the axial forces, so we're going back through a process of confirming that. So you got the reactions, right? So now we can properly size the connections. And then looking at the principal stresses, I mean, you want a good uniform character to these surfaces and the stress profiles. Principal stress is 2. Shear stress. Shear is important. In other words, you don't want the panels, because you're connecting on the corners, you don't want any of them to translate one another. And so your shear is an important one to check. The Mises forces, moments, and then the revised geometry. So we've gone through a process of revising the geometry. We're looking for tighter performance, better deflection. And there you go. You can see the geometry. It's maintained. You're not seeing it's not blading out. And so we have good performance within that surface. So I said there's a method to the madness of actually going to the membrane. Why not just leave it a cable net? Well, because we wanted to panelize it. We wanted to use panels, and we wanted to do something nifty. Initially, the surface was just these overlays of plate material. We talked and we talked and we talked and said, well, what happens if this could be furry? And so we devised a way that if you actually cut these kind of Cs and you bring them together, you get this kind of a loop effect, and it becomes this kind of furry surface in the process. So this is just the panelization and the element development. So this is one panel ready to be sent through the fabrication process, CNC. And here's it going installed. So each one are uniquely numbered. And you can see how the furriness happens. Effectively pull it together, and the surface bends out of shape to create this furry characteristic. It's quite tight, right? So, I mean, without knowing exactly where you are. This was built by students, so it was one of those very, very interesting projects to work with students. So the next project I'm going to talk about is, it's a bit different than all these crazy form kinds of things, but equally difficult. This is Michael Heiser. This is a levitated mass. And it's one, if you're reading the paper or watching television, everybody's talking about it. They're going to move this big, big rock from a quarry, western LA, or eastern LA, to LACMA campus. Well, this is the boulder. It's massive. They have to shut down the roads. They have to move it at night. And they're going to install it and then have this big kind of party for this piece. Well, how do you design something custom for a big rock like that and know that you've got what you've designed ready and able to actually load up this big rock? Because you've got something that's very unique from a geometry point of view. Well, we scanned this rock. So we scanned it digitally. They lifted it up, they scanned it, and we got the digital information. So this is my first meeting. That's Michael Heiser in the hat, out in out in Nevada. You have to fly to Las Vegas and then drive 6 hours to go see him out in the middle of the desert. He's completely off grid in an outpost, just making stuff, and it's really incredible. And he's old school. I mean, he's like making stuff by hand, super, super precise. He'd never worked in a real digital process ever. And this had to happen. To take a rock and move it somewhere and know you could just drop the rock on this trench idea was a big step. So this is his mock-up. This is the idea, and you can imagine this conversation. I have this big rock. I want you to engineer me a trench so I can drop the rock on top, and I'm going to call it levitated mass. It's funny until somebody realizes that that costs millions of dollars, and you're either right or you're wrong, yeah? And that could be a real big crisis. So we scanned the rock. How we got the rock is actually through that 3D scan. So I showed up with the rock. So I had the rock scanned, and I came on the plane. People looked at me very funny, and holding my rock. And then I showed up, and he had this trench, and luckily the rock and the trench somehow met. So this is levitated mass, the rock, the trench, and you're supposed to walk under it. There's your sketch. There's under. And there's the lay of the landscape. So that's plan, right? That's all you get. That's the idea. So we had to be very specific. We had to have the digital survey. We have the site, right? What is the run? I mean, there's all of this geometric information that has to be embedded. What's the code safe for a ramp? What's the code safe for a landing? All of that stuff had to be plugged into there to actually develop that. And that had to be presented because there was an idea of art and how do you merge the two and make everybody happy. And you can only imagine my conversations with the city. I want to do a rock. I want to take a rock. I want to put it over a trench. I need a building permit for this. What do you think? The juggling and ultimately what they said, this is a building. By the way, so the city understands this as a building. We pulled a building permit for it. So we built a Rhino model, so we kept everything in Rhino. We have the geometry, which was a 3D scan, and we could work and ultimately evolve this geometry. We had to go back. Don't ever do this. Make sure you get more information than not. 3D scans are expensive, but they're super cheap relative to lifting up rocks. We did it twice, which did not make LACMA very happy. But obviously on the bottom side, how the rock lands on the top of the wall is super important. And the detail of that the resolution of that underside scan, super important, because you're going to have to shim that. We're going to have to put in shims to support this thing up so that the rock is stable. Because there are these things called earthquakes in California that the building department was incredibly terrified of. So there's the 3D scan. You can see how the rock is landed. So this is effectively your approach to the rock. You see the two plates. So the plates sit on top of the wall. The plates cantilever in. And so we're worrying about what is the relationship between that plate and how that rock is going to come to bear, and how do you actually create bearing, uniform bearing in that. So that's looking from the side. So the rock looks good when you're looking at it forward, but not so good the other way. There's serious overturning in this thing. And you can also see how it's actually, the rock curves on the underside. And huge arguments about what the seismic force is, what's the overturning, and what's an acceptable bearing, because there's nothing in the code about stone as a structural material. So we had to get a whole party of geotechs together to agree what an acceptable or allowable state of stress is in rock. We had to get a whole other party of structural engineers together to agree what acceptable overturning is and how you actually transfer those forces through the system. So there's your scan. This is looking on the underside, and here's your projection of those plates. And because we had the geometry of the rock, we have the plate, we could actually now begin to spot grout and the shims to effectively lock the rock into place. And then we weld the shim, right? And why this is important is because the city wants to know what that is. They want to know how long a weld are you going to actually, because they're going to come and inspect this thing. So you can't just go out there, land a rock, and do whatever you need to do, and then at the end go push it and say, okay, it's stable now, we're done. That's not, you've got to build what you have on your drawings. You've got to build what's in your documents. And that's the risk, that's the complexity. So this is the analysis. So we did this in ANSYS to look at the overturning and the distribution of stress on the grout beds and the shims. Blow up details of that. And then the details of actually designing the shim, meaning we have to be spot on. As I said, the city wants to know what is the shim. You can't just go out there and chisel on it and ultimately arrive at, well, it's stable now. It's specific. So to build up all of that. And that's all geometrically modeled 3D information, virtual prototype. And then, again, I'll always go back and I say, look, you know, so we got the rock landed on some plates, but then there's this concrete piece. It's a piece of art. It's not a piece of civil infrastructure. What's it look like? What's it feel? What's the finish like? You got to mock these things up. So we went through a whole world of physical mock-ups, digital mock-ups to ultimately arrive at the final solution. So that's the mock-up. This is the grout bed and an anchor for the rock, anchor going on the underside. And then the buildup of the shuttering for the rock chamber and the details. And you know, this thing's so precise. It's a piece of art. The expectation's so tight. When you go to construction site and the expectation of tolerance, I mean, you could get things 5 foot out of line. And being able to go there, so Ron Elad was the field engineer on this. He went with an iPad, so he had the digital model. He could drill up whatever information he wanted using an application one of my guys created called GoBIM that allowed him to drag in real-time 3D information specific to the location so he could inspect it and make sure that we were on point. So there's the chamber. You can see the shelves that effectively pick up the rock. Massive. So we're waiting a rock. So yeah, that's soon to come. That's the Christmas present. They're going to drop a rock on top of that. So it seems like it's moving out. We're already a few months late, but hopefully we get a rock soon. The next project I'm going to talk about is a project, I've done a lot of these actually. This is a material study at SCIArch that Tom Wiscombe, he's run a materials lab for many, many years. And I've worked with him in this materials lab, I don't know how many years, I guess since I've ever come out, 2006. And we've always explored very complex materials. This one wanted to explore the idea of composites and using some kind of very extreme amorphic kind of architecture. Because if you know Tom, he's always interested in these kind of emergent systems. So the one thing he said, Greg, what is the one input you can give to the students to put some intelligence to making some weird amorphic thing, but yet have some emergent structural behavior? Well, he always starts with the cantilever because that's the most difficult, right? And I said, well, you know, if it's a composite material, you've got thickness controls because you've got cost. Why don't we play with folding? What happens if you fold, and what does folding do to stiffen up this thing? And so this is the mock-up of the what was a semester's work of study of finding this shape, this form, and then the second semester they actually build this thing. So that's that. This was the conversation of how do you make a stiffening rib on a surface. This sounds great. This looks great. This looks like an engineer created it. And this is what they did. They're like, well, we want some parts because we can manufacture it, and we're going to fold those parts, and hopefully it has good behavior. We worked in a Rhino ANSYS interface. So we used Rhino geometry, and we just kept pounding it through ANSYS. ANSYS is a high-end finite element solver, which ultimately allowed us to play around with where the ribs are and what the attachment points are. So parametrically, we just worked our way through good supports, rib stiffening, and they always had some clear idea about what this cantilever was going to be as a formal thing. And so this was a small model built up. The orange piece is really some taping, so it has nothing to do with structural. It's purely an aesthetic. Tom called it a tattoo. So that's what the tattooing of the skin is. That was the mock-up, so that was a semester end. They built this. So the original mesh, so when we started this thing, we take the Rhino geometry, pull it in as a surface. There's some level of meshing, right? The meshing basically defines the surface, allows us to look at that surface and actually begin to understand through the analysis process what the interaction is between each of the mesh elements. Something this complex, you have to go through a process of refining this mesh, and you can see the density of meshing that's actually happening. Now, you just don't want to let this thing go. You don't want to just maximize the mesh, because the more dense your mesh, the greater the computation power you need. Meaning, at some point, you'll extend yourself well beyond the computational power of the computer and or the software. So you have to really, 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 really be frugal with your decision making and how you do it. This is iteration after iteration after iteration of refinement to actually arrive at this mesh. Still dense, but to arrive at that. So this just shows the logic of that. We've written a whole world of scripts and tools that effectively help us mesh. So we're looking for characteristics, and specific characteristics will then intensify the mesh in localized areas. So you can clearly see that, you know, anywhere that you get an edge condition, that mesh really gets quite dense because it's attracting stress because of its stiffness. So again, looking at the mesh development. So then the analysis, really looking at deflections, but I'll show you factors of safety and as well, and mode shape and mode. So this is gravity. So of course the tip is going to be the greatest deflection, which is here. The supports are the blue, obviously. What happens when somebody hangs on it? And we actually tested it. One of my guys, JP, who's a college mate of mine, jumped up on top of it and started bouncing on it. So thank God we did the dynamic piece. So that's the tip. Loaded loop, what happens when you actually have a weight attached to the loop, which is this piece that extends out. Then these are the mode shapes, and we're really looking at frequency issues, wind. You say it's in the building, but because it sits next to those double doors where you walk down the main hall, actually, and people prop that open, on a good windy day, you could get some pretty good. So clearly you want to pay attention to the dynamic phenomenon. And then ultimately when you're dealing with these kind of surface things, and we didn't have a building permit on this, so because it's quote unquote temporary, we look at factor of safety. What's the factor of safety for the stress state? And this is basically looking at a mapping of the factor of safety on the surface. And obviously the blue is the best, the red not so good, and we're ultimately working to refine that stress distribution to get higher levels of factor of safety. So this was the mock-up. So we built a mock-up just to make sure that we got good quality product, tested it from a strength point of view. Ultimately got to the detailing and the manufacture. So this is what the taping or the tattooing looks like. What it looks like with light coming through. You can see the ribs, how it stiffens. It had to be of weight that they could lift. There was a limitation in what they could actually lift into space or hoist into space. They had to assemble it on the ground and then mount it to the points, 3 points. The hanging engineer, dangling. And then the piece installed. So this is still over there if anybody's interested in seeing physically what it looks like. The next project I'm going to talk about is a project that I've done with Cliff Garton. He's known for doing these totems, stainless steel wire totems. This one is in Dallas. It just got installed. It has a height to width ratio of 13, which is outrageous for a tower, high-rise tower. So obviously wind. This is an outdoor installation. And I love these projects because, you know, it's pure engineering, pure structural engineering, and incredibly fun. So Cliff has a whole world of these really, really talented guys that have come out of industrial design that build these really beautiful wire models that then he can print beautiful 3D prints of things, and then he sells these things to very rich benefactors who then are willing to build these things. That's great until somebody says, yeah, I'll buy that, but that's a very difficult proposition actually to render it in stainless steel. Yeah. So Cliff came and we sat down, we figured out how we might go about doing it, and this is really the story of how we did it. This is the city center piece. We built it up in CATIA, so it's all described. The system works, it's a torque system, so, and I'll show more details of it. Effectively, it's held together. These things, these lines effectively act as outriggers. So there's a central core, and then these outriggers reach out to the perimeter skin and really tension it up. And so that's what gives us our lateral resistance. And these things torque out. So ultimately, the fabricator, all he wanted was CNC files. He wanted us just to say, this is the amount of wire you need, the CNC file for these outrigger pieces, and then the rod, and then he was done. He was just going to assemble. He didn't want to think about it. He didn't want drawings, didn't want anything. Just tell me the parts. I'll put it together. So this is the model we did to do that, all in CATIA, all the plates that hold it into place. This project is difficult because we're cold bending the stainless steel. So if you can imagine, if you twist something and it's got vertical elements and there's stiffness, as this thing rotates, there's rotational stiffness and it wants to untorque itself, right? So we're fighting that, which we resolve by actually putting in this internal core. And this better explains it. So you can see how these things rotate as they go up to develop this kind of thing. And so you can see this central core, and then you can see the wires that effectively go around. Ultimately, at the end, then there's a light, an LED light, very high-powered light that goes up through the center and lights this thing up. And because it's highly finished stainless steel, it glows. So the structural analysis, getting the information into structural analysis is difficult, and different jurisdictions always want to have different information. In this case, we use SAP. SAP is more common on the West Coast, predominantly a US product. The city, or the building department, we had to get a permit for this. And they understood it as a skyscraper. Not an art piece, not a monument, but they understood it as a skyscraper. So we went through the whole process of doing that, had to produce calculations, and we pulled a permit. We proved out that under wind it'll move, but it won't excite and take off or fall apart. And then we went through the whole stress piece of actually engineering all of these elements so they were right-sized. So there's our stamp drawings for the city, and the piece drawing and a section of it. There's it fabricated in the shop. This big central core, anytime you're building things like this, you have to think about how you're going to build them. And I can tell you, I've seen art of large scale where they've built it in the shop in one position, namely on its side, and nobody thought how they're going to write it. Millions of dollars just lost. So that's that. That's the anchorage. So it's got a central core, anchor bolts, attaching it to foundations. We shipped it in a truck. So it was manufactured in Utah and shipped to Texas. And you can see the rod. It's simply just bolt. This rod goes all the way down to the base. It bolts. So once we get it vertical, we unbolt those 4 bolts, and the thing just literally lifts right out. So we need a fairly high crane. Also important to know what equipment you need to install. So there's it going in. There's Cliff checking it out. And there's it lit up. Okay. So inevitably, I always stand at these things and talk about complex art pieces, and somebody will always say, well, what about buildings? So I'm going to talk about a building. This is the Anaheim high-speed rail station down in Anaheim. It's for those that don't know Anaheim but have driven past, which is probably the better choice. I hope nobody's from Anaheim. This is right by the A's ballpark. What's interesting about this project, I think, is that the city wanted iconic architecture. They went with a very non-traditional American approach to building, meaning from an environmental perspective, it's a really pushed design. It's a LEED platinum building. It's got an extended comfort range. So with that much glass, very, very difficult to actually keep it tight band tolerance from an ASHRAE perspective. So you got to extend that. So you got to accept a different level of performance. But it's a rail station. People are going to pass through it. So does it need to be conditioned like an office building? Probably not. So all of that went through. It all got approved. And costs became prohibitive, right? You can't do glass. You can't. And the discussion went, well, what about this stuff called ETFE? Well, those are those pneumatic pillows that you see the European guys do. And this one, in this particular case, that fit the budget, about $150 a square foot. So I'm going to talk to you about this building and the enclosure and how you arrive at it. It is, you want to say it's a barrel vault, but it's not. It actually is doubly curved. So the side walls are doubly curved. The roof is doubly curved. The front is 120 feet on the facade, vertical face. It's 90 feet on the backside. So that curvature just makes everything incredibly complex. Probably the most simple piece about this project is actually these curved 120-foot glass walls that are hung from above. which, interestingly enough, when I started the project, I didn't think that was going to, I thought that was going to be the most difficult. To hang 120 foot of glass is a big challenge in and of itself. But it actually proved that that was the most simple, and actually the most complex was the sidewalls. And I'll talk about that. The story goes something like this. This project for me, I inherited it in DD. We had 6 weeks to complete. The architect was struggling. They had developed a geometry, but they hadn't developed a geometry that they could understand and develop, meaning they couldn't come up with a panelization strategy, they couldn't put it in documentation form, couldn't handle the complex geometries. Initially, they went up to Autodesk and asked for help. One of the mandates of the contract was that the documents had to be produced in Revit. They had to provide them a Revit documentation set and a Revit model. Well, Autodesk says, whoa, you're not going to be able to draw this project in Revit. And all of a sudden, the panic hit. One of my guys, he has this digital forum, and I forget the exact name of the title, but he has a digital forum. He gets together and has lectures, principally at UCLA. He gave a lecture. It was actually Ian Keogh gave a lecture talking about tools. And HOK principal designer came up to him and said, hey, you know, we have this problem. We have to deliver a project in Revit. Autodesk just told us we can't deliver it in Revit. What do we do? I think he was showing the Eckelmann piece. Ian said, well, I think we might be able to do something for you. So that next day, Ian, I, and Kurt went over and we talked out a process. How would you take what their iconic vision was, their drawings, and actually push it through into something that could be engineered, priced, and understood? And this is the process that we ultimately arrived at. This is the geometry. We built it in CATIA. So it's all built in there. It's all centerline geometry. That centerline geometry is now the baseline communication for everybody. So no matter who we're talking about, we all are operating in the same digital realm, same digital information, and everybody had to build on that. Yeah? That was huge, because up until that point, everybody was kind of making their own stuff. The complexity of this thing, you realize, actually, and you can just see it in the diagrid roof structure, is the deviation of the radius as it cranks itself around. So super, super, super complex. This thing is constantly torquing itself as it's going around. So we have that information, the centerline geometry. We can now develop the 3D object families for that surface. So there's the pipe of the diagrid. There's the channel that's actually going to hold the ETFE and the clamping mechanism going to attach to. There's the gutter and the sidewall. And then we can keep independent, for the moment at least, the end walls, because these are things in and of themselves. So there's your entire database built up on the side. There it is in plan. And we were working between Revit and CATIA, and this was just really a test to make sure that we could get that geometry in early, actually check the structural analysis, so we can actually get that information into Revit through a link. So the geometry of the roof, this is the normal arrow to the surface. Each one of these tubes is effectively just tracking that surface. Yeah? The problem with these arrows is they're actually slightly rotating apart. So if you kind of did an array, they're always kind of marching along that way. So they're always pulling apart. Well, if you've ever done an aluminum extrusion, or you know anything about an aluminum extrusion, you can bend them, you can torque them to some degree, but you darn well can't do a lot of torquing and a lot of bending. It just won't happen. And so this was a huge problem, and how you're going to actually resolve that. And this was one of the first big problems that the fabricators started to say before we were appointed. They're like, well, we don't even know how we would even bid this if we wanted to go design build, because we don't know how you would resolve that piece. So we actually worked and we pulled off some logic from Sealy. They used it on the Munich Stadium, Allianz. I'm going to tell you a little bit of the story about why this thing doesn't work. So this is the track. If this track just tracks that geometry, so it doesn't rotate to stay normal. So this is what you end up with. This is the top, this is the crown of the shell, and you end up with this clash, meaning, in other words, they don't come together, and so you can't close the roof. You can also see what happens if they just continuously track. You can't make a node. So you can see the node clashing. There's a blow up of the node. So you couldn't even drain that. So this is the detail that we used from the Allianz project. This is an EDPM gasket. The ETFE foil. The foil is like sheet material, so flexible, and then aluminum extrusion. And we could segment the extrusion. So we still got the tolerance control of the aluminum extrusion, but we could now handle it through the pipe, a chair, which offset it from the structural pipe, and then a channel in structural steel. And because it was a channel that had flat surfaces, we could actually build it up from plate material. So we could effectively unfold it and actually have a developable surface, meaning we can cut it from flat stock. Now the torquing element completely eliminated from the project. So that's how we arrived at it. So this is the unfolding of that channel. And then the development of those node points. So there you've got to do some cold bending to actually develop that node because you're dealing with two geometries. But we can check that through a tool in CATIA to see what that extreme case is and make modifications accordingly to make sure that they're still within a cold bending position. And then here's that drawing again. You've got the normals, you've got the channels, you've got the nodes against the structural 16-inch pipe. And we now have an entire system that now is ready to be clad with ETFE foil. And here's how it arrives at the ridge line, or sorry, at the gutter, the sidewall, node, top, and the details. Again, we're always working in this virtual prototype mode. It's hugely important. You can easily get yourself on very large projects and very complex projects where you need a mock-up, a physical mock-up, and that physical mock-up can be $3 or $4, $5 million. Yeah, and oftentimes you're fighting that. I mean, you're talking about a mock-up you're going to make and then discard, right? Because nobody will ever allow a mock-up to be incorporated in the work, or they shouldn't, particularly if you're using it for testing. So virtual prototyping is an incredible way to actually make sure that you get your tolerances, you get your connections, you get your details developed in a way that you want them. You can also begin to start to check for performance, particularly in structures. We can test, and Anders' firm, SCIArch, does a lot of that virtual mock-up testing. So this is just the details of that being developed. So here's the conduit. ETFE, these pillows, they're pneumatic, so you're supplying about 7 pounds per square foot of pressure. So not high pressure, but nevertheless you're supplying it. So here's the tube that connects it. That's 3 layers built up, so it has two cavities, and that gives us structural properties. And then the detail of the crown and the pillows. So this is the analysis for the pillows. Here's the structural analysis for that. So we're looking at stresses within the films, the fill and the warp and the definition. What adds to the complexity of this is you have curvature happening in the same direction. Typically, you get a pillow positive and a negative curvature. So you got to deal with you got to worry about the uplift condition. We actually initially built-in slip cables. So 3.5 kilonewtons is the maximum stress ETFE can take at 250 micron film. There's 300 micron available, and then there's thinner sheets. 250 is the more common. 3.5 is the breaking point. So you can see we exceed that with no slip cable. And with a slip cable is nothing more than a real cable sandwiched into a pocket within it's a piece of material welded on top to create a pocket, and the cable goes into it. That locks it in, and that deals with our uplift and downward pressures in the extreme cases. So we could identify where those cables go. Now we have developed the formal characteristic of that. Because we were moving very, very quickly, this was an early design assist package, we could develop the worst case and then predict within reason what the shapes would be. And this is just a script that's been written to actually populate the rest of the pillows. We knew what the worst case was, now we can just propagate it. Project's gone another route now, so we actually are doing the detailed patterning of these pillows. And we're actually been working with the fabricator, so it goes back to my story, always bring in the fabricators early. We've worked with Gartner, Sealy, and Vector Foil to actually say, look, you don't need the cable, you don't need the slip cable any longer. Let's just double up the sheets. And as long as we know geometrically that the material are actually sandwiched together and that geometry is perfect, yeah, then we know they're going to work as a coupled system. What you can't have is one more stress than the other, otherwise you're going to pop that one, and the one that's not tension won't fail or won't carry its proper load. So you need them both uniformly tensioned. So we've worked with those guys to now believe that we can actually layer this and eliminate the cables. So now we have the pillows. We can load those into CATIA. And through a little magic, we have now ported this into Revit. So we've now satisfied or helped them satisfy a key component of their contractual requirement. So it's now in Revit. These are CATIA shots of just the details, so we virtually mocked up all of that stuff. So now we're in Revit. We've got the definition. And we need to work on these side walls and the end walls. So this is the side wall. And as I said, I'm a big advocate for being software agnostic. So we'll use whatever tool is necessary to get the job done and the best tool to get the job done. And obviously on a sidewall where you get loads of subtle geometry, loads of layered information, Grasshopper is a great tool because you get the parametric functionality of Grasshopper embedded in Rhino, so that you get that. Middle screen is effectively the Rhino model of that surface developed as 3 layers, and I'll describe that 3-layer system. And then the clashes between the vestibules protruding through that wall system in definition. Once we develop that geometry, once we can define that geometry, we now have functionality within Revit to import that geometry into Revit, and now we can work on developing the wall. So that's the buildup of 3 layers. The 3 layers is there's a secondary structural system to support it. We unitized it on a module of 4x10. So that's the second layer. And then the third layer, because it's got this faceting that's happening, and I'll talk a little bit of why there's a faceting happening, we put a louver on to cover up those facets because you would always kind of see this fish scaling, and it wasn't pronounced enough to look like it was designed. It looked more like the panels were out of alignment. So it was an overlay to actually cover up that there was some real problem with the fact that nobody really caught on that doubly curved surface needed to be rationalized in a way that accepted flat panel stock. So just to go back, tools, this tool development, this is Revit and Node Tool, and just a drop down of things that you'll find in our Revit version of how to bring in information back and forth. So this is the sidewall, and this is the assembly. You can see here's the vestibules popping through, so that has to be coordinated. You need all those tolerances. Here's the unitized panel, so that's a 4x10. Here's the panel. It's a combination of metal panel, perforated panel, and IGU units, glass units, insulated glazing units. And then some complex geometry in terms of these fins. And these fins, because they're aluminum, they have to be extruded. So again, they're faceted as well. So the complexity just gets bigger and bigger and bigger and bigger the more you lay this thing on. So we can bring in all that geometry into Revit. We brought it in. That's the buildup, the bigger buildup. To define those panels, how would you do that? Well, this is the elevation, and I'll talk a little bit about why the panels, or the flat panel piece, didn't work. Because there was this difficulty about working in Revit, at the end of the day, what they did was they elevated the elevation, and they drew a 4x10 grid, and that's what it was. Completely not considering that there actually was double curvature, and you had to pick up all of that faceting that had to happen. And it was a late in the day change to go and revise the architectural design. So we pushed it through, and it was only through our work that we realized that maybe we should cover that up, because it's going to look like you got a world of panels that nobody installed correctly. So we defined, so this is the elevation of this panel, the node points, the definition of those nodes, and how we described it to a fabricator, curtain wall fabricator, where they're going to put these panels, where they're going to put the node points on that face. And because this wall is constantly warping, so in other words, it starts this way, and as it works its way back, it's constantly tilting in, so it gets flatter in the backside. We had to describe unique at each of those joints what that geometry line was, and we cut it as section. So that's that definition. So the project went out to bid. The curtain wall guys were like, wow, that's a super complex system. Why didn't somebody rationalize it? And we said, yeah, that would be great. Let's rationalize it. So we've now gone back, and we're in the process of redesign to rationalize this thing. This is the new rationalized elevation, pure panels. You don't see anything, and it just goes smoothly around. Flat panel stock looks curved, The other thing we took out was, beforehand, all of the fascia, this metal panel stuff, along the edge, and then the cover at the end walls was all curved metal, which basically meant you had to go to a body shop and get custom coachwork built for this thing. You can only imagine what the price tag came in for this thing. We now are getting numbers back into the, so there was this number, there's our current number. We've got a factor of 5 between the two. So we've brought it completely in, bringing fabrication intelligence into the process. And this is just a shot. Obviously, when you have a client, he's bought a project, he's very excited about it, and they say, well, geez, that's a great idea, guys. Thanks for giving it to us, but man, that's going to change my design. I'm not happy with it. Well, all of this is showing is what the deviation is from the original design. And it's just the pink bit that's the deviation. And you can tell that because of the little fluting bits up here, we've cleaned up and actually do have the resemblance of double curvature in the panels. So the final piece is now how do you get these end walls in? And again, working in the early days of a project and then working at the end, you're always trying to figure out how the assemblies go together. So we're looking down in plan. We've got these columns that are going to pick up this line of support, which is this pipe. That's the column. And we're going to locate the face of glass, which is the pink line, and then support that face of glass through wind load back to the column. And then the rest of it's going to be hung through stainless steel rods from above. 120 feet of glass. So there's your columns. There's your face of glass. And you can imagine you're trying to align face of glass with a roof system that is pillows. You know, how are you going to close that? What's that closure? How do you actually know what that closure is? One could imagine and draw a detail, but as you go around, that detail's always changing. It's never the same. You need to actually effectively draw it every time. Well, if you had to draw that every time, you'd just say, forget it, let's just do another building. To do it digitally actually gives us that ability. So here's your new fascia, faceted, going all the way up. You can see these are flat panels, and you can actually see that effectively follows. You could slightly see that they're flat, but I promise you that they're flat. Here's how we reworked that inside to get these flat panels. You can now see the glass, actually how it's going into the edge. Another misnomer was, geez, let's unitize this entire facade, it'll make it super cheap. Well, unitize means that you got a factory and you can just plug product through. Because of the curve, you have so many unique pieces, there's no value in unitizing. It's better to build this thing piece by piece because you're going to hang it anyway and you're going to tension it up. And so we've now moved our way into a stick-built system. Here's your virtual prototype, early days. So this is literally hot off the press this week. The faceted fascia, not to be confused with the Turbo 3D version of the faceted building. The detail coming around, the pipe, the chair, and the channel, and the foil. The next big piece is 120-foot wall. Is the structural analysis is quite important. And the reason why this sat independent for a while was the structural implications were huge. Where do you find value in this system? Obviously, the curvature in plan, it's an arch. We get stiffness out of that. We want to use it. And so we want to look at the entire glass wall as a structural system as opposed to just a component. So in other words, we don't want to look at it as tension elements attached to armatures to a column and just look at the local and size it that way, right? Which would be a typical approach. That's not a value approach. So we modeled the whole wall. We used Grasshopper to generate the geometry. We're going to Robot. Robot actually has a pretty robust solver for complex geometry, so we're in Robot. So you can see the columns loaded. We panelize it so you get the panels in there so we can actually collect wind loads. So we're going to run this thing. We can get the details so you can see the armatures. This is the old model when there was armatures at every 4 feet. We've now eliminated a lot of that, and I'll show you the final. Here's your bending moment in the backup wind girt. This is the horizontal transom that goes around. This is the moment within the column. And this is the visualization of the deformation. Why is this important? If you actually are talking envelope, you worry about what that joint is in the performance of the joint. How much movement am I actually dealing with? This is the visualization of that movement so that we're all very, very clear early on what the building is doing, what's happening at the joint. Here's the numeric part, so we can look at the componentry and actually understand what's happening at the component level and actually understand what's the deviation or the variation, the differential between components. And so now that's the wall, or that's the entire assembly built up into Revit. So you got the end wall, side wall, ETFE, faceted panel, all plugged in to the model. And as I said, early day on the sidewall, but value add. And then just a blow up of the detail, here's your tension rod. So effectively, gravity is being handled going up to the large vault. And then looking at the elements, again, you can take a look at these things purely in a simplified way, or you can take a look at it in a complex way. We're cutting these from plate steel, so another value-added feature. Before, we had all this customized aluminum stuff, but you can get really, really high quality product using CNC process, cutting it out of plate material, and then just doing a relatively nice finish on that material. So we're sizing those. And then there's your final building without a roof, just to show the end wall cases and the side walls. And then your final picture. Thank you.
projects as they were given, there was incredible feedback through the kind of testing of how it actually could be built and a kind of refinement of the strategy to do that. But I'm still totally unclear as how that feedback that actually affects the kind of formal conception that we get. So the kind of initial conceptual form seemed to have been kind of presented. And then you became, in effect, an enabler of that form. But my question is how does this get feedback into the kind of formal conception?
Yeah, that's a good question. I consider myself very much an enabler. Yeah, so
I think that's a tremendous compliment.
Yeah. No. And I think. Yeah, exactly. I consider myself an enabler. Yeah. Not exactly what I thought I would ultimately be. I always had high ambition. I was going to be an architect. But I actually find working with a variety of different people doing a variety of different things is a lot more fun and a lot more interesting and a lot more challenging than just trying to replicate my own interests, yeah, from a pure design perspective. So that's probably the first piece. And it was really it's interesting, it started out of really a frustration when I practiced architecture that I just never got any dialogue from anybody. You know what I mean? We had ambition, but I never got any support. You know, I couldn't find those folks that would really engage. So I really custom tailored my career around that, and it seemed like there just hadn't been a lot of people interested in how to deliver things. They like to draw them, think about them, big idea, but not do it. So that's that piece. Oftentimes, you know, there's this kind of initial sketch, yeah, and sometimes it'll be a conversation. Sometimes that sketch is already pre-hatched. It'll be pre-hatched as some kind of idea, and they'll grow it up, right? So in the case of Michael Heiser, he had an idea, but how big, yet to be determined. And big was the piece that I participated in there. In the case of Tom Wiscombe, he has an idea about material and an idea of form, and he's interested in emergent behavior within that, and that's the participation in that. So I think, and I could go on, there's variations of the theme. I think everybody, everybody has their own way of working, which I think is kind of fascinating. Some people, they never have an idea about what they want, and you sit down and you'll sit there with a stack of paper or a roll of trace, and the idea of a project will be hatched in this kind of dialogue. And that's a really rich thing. I didn't really show those types of projects because I really wanted to talk about the kind of the digital piece. I think it's more common, and I think it's probably endemic of the architectural education of the black cape and beret mentality that there's the singular vision and then somebody else is going to figure it out for me. I think that's more the problem and more of an indictment of architectural education, that it's not it's not understood as a collaborative endeavor, and not taught as a collaborative endeavor. And many, and I have it in my studio now where, the students are struggling with a piece of software and they see it as themselves in that kind of interpersonal, it's all me struggle. They don't reach out to others. They don't actually reach out to other studios. They don't go ask for questions, what do you think? Because they don't understand what that collaboration piece could bring to their project and how that might help them get out of their troubles. So that's the kind of takeaway from that. But you're right. Most of it comes to me. Most of it comes to me in my studio in a way that is, this is the idea. Now, what do we do with it? Now, the richness comes thereafter. You've seen me lecture on the Smithsonian Patent Office, for example. I think the beauty in that, particularly if you talk to Norman Foster about it, is actually the resolution of how do you panelize it. You know, the curved surface is beautiful, the 3-vault roof is beautiful, but actually it's the panelization, it's the faceting, that's what took it over the top and actually makes it special. And that's something that came or emerged out of that process about how do you panelize and develop an idea. And I think that showed in the CCA aortic arc, the light shade piece, because that was very much a paper mache kind of lampshade, and it became something so much more rich. And in fact, the form they gave me was in a Maya version. Janet Eckerman worked in Maya as well, which, if you know anything about digital computation, Maya is just an incredibly poor digital tool. It's horribly inaccurate. So you have to rebuild all that geometry to get to something useful from a fabrication point of view. Did I answer your question?
Yeah, I'm just wondering whether in the end this will result in a kind of new, kind of typological reference where the kind of refinement and implementation basically develops a new type, or whether this process basically lends itself more to a kind of reiteration of new formal resolution.
Yeah, yeah. I think that piece is interesting, particularly in the work that that I was doing with Roland Stokes in last studio using Process Bot, which is a application that he and I wrote that effectively takes structural fitness criteria and working off of his ideas about agent-based development. What does a system emerge as a structural system? Yeah, so I do think there's new, and Tom's work is pretty out there in terms of these emergent phenomena. So I think there's another point to that, which is important for the students, is that I think there's a new hybrid, actually. I think engineers aren't equipped to operate in this domain by themselves, and I don't think architects are truly capable of operating in this domain. I think there's a hybrid. One of my legacies, my partners in Buro Happold would say my real legacy in Buro Happold was I invented the technical designer role, which principally is everybody not an engineer, but enabled at the same level of an engineer, meaning you're not the CAD guy, you actually are somebody that participates in the process, and you bring to bear some specialist skills. And there's Krista Laney, who's a USC grad. She's one of those folks. I have a few from USC, have one from the AA. And then I have some folks that, math background and database, comp sci guys. And, you bring these together really to enable that process. And I think that new hybrid, those are the emergent jobs, or the emergent field, or the emergent careers actually happening in the AE industry. I think there's real value for people with depth skills. Architecture is great in making good generalists, but at the end of the day, there's a lot of generalists. What are you going to actually bring to the table in terms of actually a real specialism that's really going to enrich the process, knowing full well you've got to work collaborative if you're going to do anything of real substance.
We have a new degree, archineering.
Archineering.
Let's continue on that hybrid kind of significance of the role of hybrid. Is there kind of the realm that you could clearly now map out where your hybrid role could develop into researches that actually accumulated or congregated into a set of knowledge that is then became much more fundamental, more than the dynamic practice platform could enable?
That's a good question. I think you're seeing it in, the dean and I made a trip to Georgia Tech earlier this week, went to go see Chuck Eastman. And I think clearly that is a paradigm shift in how we are actually going to. For those that don't know, Chuck Eastman wrote the handbook on BIM, and
probably single-handedly has the most funded research of anybody in that kind of digital realm. And he's really working on building processes to standardize. Now, standardization can be bad. In my case, I argue against it. But standardization can always elevate the field. And I think, those moments of standardization actually are do justice to do such a thing, which is elevate the field. I ultimately think if we don't pick up on the BIM side, the contractors will do it. I mean, you can go to any major contractor and they've got whole teams doing BIM modeling. And if architecture doesn't understand the world is becoming more complicated, more sophisticated, and that they got to work with other folks and work intelligently with other folks and be able to document it and integrate it into the process, the contractor is just going to take more and more and more and more, and the only thing architects are going to have left is scheme or concept, and then somebody else is just going to render it for them. And I think that piece is actually where research for architecture can really happen, because we need to make those big steps now to reestablish architecture and the field of architecture really as the cornerstone to the master builder. Not the individual, but the field of architecture, the field of engineering linked up as master builder. And that the contractors really become participants in it, not dominant in it.
I also want to address the kind of work ethic you have with artists and particularly emerging young designers in Los Angeles, in the region. How do you see that role plays out into a kind of activism in the creative community, and how do you see that role plays also into a pedagogical or even a academic leadership?
Yeah, that's a good one. Really three things. One, I recognize I'm really quite lucky growing up in Nebraska, having met some people during college and been given the opportunity to actually effectively become a partner in Buro Happold. I think Buro Happold is an incredible ground. And so as an owner, I feel some obligation to the community to actually support the young generation, the young designer, because I think it is really, really hard to do innovative, progressive work without enablement, right? Nobody can go out and buy $75,000 worth of ANSYS software or pay the $40,000 license for CATIA, and that's a challenge. And I think the lineage of SCIArch installations and things that certainly my group has done and been involved with really has put some real serious, talented young people out there and established them to do some really, really interesting things. From a purely selfish point of view, I think the young folks are not jaded by the industry. I mean, I think part of the things that I was saying about the industry, the AEC industry, it's so fragmented. Contractor says so much about what's possible. Developer has very narrow view about, I'm saying this to you, Simon, very narrow idea about what a building is and can be. And from a purely selfish point of view, youth is a powerful thing, and to work with young designers in the most radical of idea, man, if I can get it to something that's really interesting, that's better than gold, and maybe I'm just a simpleton, but I really do like very difficult problems and actually finding a process to get there that actually executes them. So
I'm looking forward to a book titled by following Pavarotti and friends. Lastly, how do you bring this into your classroom? I'm kind of frustrated or disappointed not seeing what your teaching has been. I realize that some of your teaching has nothing to do with this. It's mostly systems and integrations. But how there's a strong sense of integration there. But how integration goes with other realm and through your teaching?
I think that is the struggle. I mean, obviously there's some fundamental first principles that need to be in play, and I would say there has to be a supporting cast. You know, you can't just do it singularly. To do a studio or to do some, let's just say, take Tom Wiscombe's piece, and something like that, that's a year-long piece, and that a year is the right kind of thing. You do your kind of theoretical exploration, you do your simulations, and then you actually make it. So design build, the hands-on piece, is really pretty fascinating. I would say here, I'd say 611, those of you that have 611 with me, you know, I'm pretty intense in terms of what you have to do and build that in. They're working in Revit, they're building that data set, pushing it into Ecotech, running analysis. They're working in physical models. They have to produce documents. They have to test. They ultimately have to write a spec. So they clearly have to understand the full gamut of what a facade is. And so, you know, that working principle, I think, is a good baseline. I think the days, the real opportunities are yet to come. I think you've got to build in that kind of base. And once people get an understanding of what you're about, what you do, and how that foundational stuff enables something. I mean, I'd love to have the guys from 611 in studio now to push something incredible on the facade side, for example. The structures piece, I haven't had a chance to actually do anything structurally related at USC, which is unfortunate, or really about the things that are really operating here in a very sophisticated way. But there are the guys that are taking studio now with Dan Meese and I, and you know, they're working with parametric tools either in Rhino or Revit that are bowl builders. So you've got to build up the numeric basis for how you establish the seating bowl configuration. We're talking about developing long span structural ideas. And not everybody's here, but I mean, almost everybody has a rather souped up kind of, very few people have the linear beam of primary, secondary, tertiary. You know, there's something incredibly formal in their structural idea. And so I think you just got to keep beating it and building that foundation of interest. But you got to build up those first principles. If they don't have first principles, you can talk a lot of stuff, but you know, there's skills. You know, to do this, you got to have some Rhino, you got to have some Grasshopper, and I think to do this stuff, I think the best scenario would be a revised studio model, which would actually be more group working, and see if we could actually get cross-disciplinary study, i.e. bring over an engineer or somebody from comp sci, and actually work within a collaborative design environment. I think it would be beneficial to engineers because I think engineers don't know how to design. I don't think they know how to be creative. I think comp sci guys, they know process and they do it very well, but they don't know how to apply process. And I think if you could bring that together, I think you could really souk it up. Because I think that's always what's missing. I spent a lot of time getting skills built in there before we actually can do something super sophisticated.
Well, I'm going to let people go who want to go. There's food outside. If you have more questions,